All right, let's dive right into one of the most fascinating ideas from Stephen Hawking's game-changing book, A Brief History of Time. We're going on a journey, a kind of cosmic safari, to track down the universe's most mind-bending creations, black holes. And our whole adventure really kicks off with one simple question. So, what does happen? We're talking about a star that's way, way bigger than our own sun. After burning bright for billions of years, how does it end? What's its final dramatic exit from the cosmic stage? The answer to that question, well, it sets up everything else we're going to talk about. Because that final act, it's the birth of a monster made of pure gravity. And to really get how it's born, you first have to understand the life of the star that came before it. For most of its life, a star is in this constant, epic tug of war with itself. Deep in its core, you've got this massive nuclear furnace, right? It's fusing hydrogen into helium, and that process blasts out this incredible energy. That's the force pushing outward. But at the same time, the star's own massive gravity is trying to do the exact opposite. It's relentlessly pulling everything inward, trying to crush it. For billions of years, those two forces are in this perfect, delicate balance. But, nothing lasts forever. Eventually, that fuel starts to run out. The nuclear furnace just sputters out. And in that instant, the outward push is gone. And with nothing holding it back, gravity wins. And it's not even close. The star starts collapsing in on itself with just unbelievable speed and force. Now, not every star ends up this way. There's this cosmic line in the sand, figured out by a physicist named Chandrasekhar. The magic number here is about 1.4 times the mass of our sun. If the collapsing core of a star is under that limit, it can actually stop itself and become a stable, dead star called a white dwarf. But if it's over that limit, well, then nothing can stop the collapse. Gravity just takes over completely, crushing the star down to a single, infinitely small point. And as that star collapses, its gravity gets so powerful, so intense, that it creates something called the event horizon. The best way to think about it is like the universe's ultimate point of no return. And this isn't some physical wall you could touch. It's literally a boundary in space-time itself. Once you cross it, every single path you could possibly take leads to the center. There is no going back, not even for light, the fastest thing there is. So how does this trap actually work? You've got to think like Einstein for a second. His theory tells us that gravity isn't really a force, it's a curve in the fabric of space and time. So a massive object literally warps reality around it. Far away from the star, light just zips along in a straight line. But as it gets closer, its path gets bent by this warped space-time. For a black hole, that warping is so extreme that at the event horizon, space-time is literally folded back on itself. Every direction is inward. Escape is just impossible. And right at the heart of it all is the singularity. This is what's left of that massive star. We're talking about a point with zero size, but infinite density, where all the rules of physics that we know, the very concepts of space and time, they just break. They stop working. And for anything that falls in, the singularity isn't just a location. It's a moment in time. It's the future. As Hawking put it, it's an end of time itself. Okay, so we've got our monster, a perfect trap that nothing can escape, hiding a point where physics itself ends. But here's the thing, that very perfection creates a huge problem. It turns the black hole into a suspect at a cosmic crime scene, where it looks like it's breaking one of the most fundamental laws of the universe. And this is the law it's supposedly breaking, the second law of thermodynamics. It sounds complicated, but the basic idea is really simple. It just says that, on the whole, things get messier over time. Your clean room gets disorganized. A coffee cup falls and shatters into a disordered mess. This messiness, physicists have a word for it, entropy. And the law says the total entropy, the total messiness of the universe, can never, ever go down. So here's the crime. Picture a cloud of gas. It's a really messy, disordered system, so it has high entropy. Now, what happens if you just toss it into a black hole? The cloud, and all its entropy, all its messiness, just vanishes behind the event horizon. From our side, it's gone. So, wait a minute. Didn't the total mess in the universe just go down? That's not supposed to happen. This was a huge problem. It looked like black holes were a cheat code to break a sacred law of physics.
And this is where the plot really thickens. A physicist named Jacob Bekenstein had this brilliant idea. He noticed that the surface area of a black hole's event horizon never gets smaller. It only ever gets bigger when you throw stuff in. And he thought, hey, that sounds a lot like entropy. So he proposed that a black hole's entropy is its surface area. But that created a massive contradiction. See, if something has entropy, it has to have a temperature. And if it has a temperature, it has to glow. It has to radiate heat. But a black hole, by definition, is a perfect trap. Nothing gets out. So which one is it? A perfect trap or a warm object that radiates? Can't be both, right?
For a while, physicists were just stuck. This seemed like a paradox with no way out. And then Stephen Hawking had an insight, a revelation that was a total game changer, and it flipped our entire understanding of black holes on its head. Hawking realized everyone was looking in the wrong place. Einstein's theory of general relativity, the physics of gravity and big stuff, was what created the paradox. The answer, he figured, had to be hiding in the other great theory of physics, quantum mechanics, the wild, weird physics of the super, super small. Now, according to quantum mechanics, it turns out empty space isn't empty at all, not even close. It's this bubbling, chaotic soup of what are called virtual particles. For these tiniest fractions of a second, pairs of particles and their opposites, antimatter, just pop into existence out of nothing, fly apart, and then smash back into each other and disappear. It's happening constantly, everywhere. Okay, this is where it gets totally wild. Hawking asked, what happens if one of these particle pairs pops into existence right on the razor's edge of a black hole's event horizon? Well, it's possible for one of them, the particle with negative energy, to fall in. But that leaves its partner all alone, with positive energy and nothing to smash back into. So what does it do? It escapes. It flies off into space. And for someone watching from far away, it looks like the black hole just spat out a particle. And since the black hole swallowed negative energy, its own mass has to go down just a tiny little bit. And this leads to this incredible conclusion, which Hawking summed up perfectly in one of his chapter titles. Black holes ain't so black. They glow. We call it Hawking radiation. They actually have a temperature, and over these unimaginable, vast stretches of time, they lose mass. They literally evaporate. And just like that, the paradox was solved. The radiation carries entropy away, and the second law is safe. But of course, in physics, when you solve one huge mystery, you often create an even bigger one. So if black holes can actually evaporate and disappear completely, what happens to all the stuff that fell in? What happens to the information? This is the famous information paradox, and it's basically a heavyweight title fight between our two best theories of the universe. In one corner, you have quantum mechanics, which has a sacred rule. Information can never be destroyed. You can scramble it, sure, but you can't erase it. In the other corner, you have black holes. There's this classic idea that black holes have no hair, meaning they're super simple. All you can know about them from the outside is their mass, their spin, and their charge. Any other information about what fell in, whether it was a book or a star, seems to get totally wiped out. If the black hole then evaporates, that information is gone forever, and that's a major violation of quantum mechanics. This was such a huge deal. It led to one of the most famous bets in the history of science. Hawking was so sure that information was destroyed that he made a public bet with another physicist, John Preskill. The debate went on for years. But then, in 2004, Hawking just came out and announced that he was wrong. He'd figured out that information has to escape somehow. He officially conceded the bet, and he actually paid up by giving Preskill a baseball encyclopedia. So if the information isn't lost, where does it go? Well, the modern thinking, which Hawking himself helped pioneer, is that the old no-hair idea was just too simple. The information doesn't get erased. It kind of gets imprinted like a tattoo on the event horizon itself. It's stored in these really subtle quantum disturbances that physicists call hair. How exactly that information gets encoded back into the Hawking radiation as the black hole evaporates, well, that's still something people are working on. But the main idea is that it does get out. And that leaves us with one last, absolutely mind-bending idea to chew on. You can think of a black hole's singularity as the Big Bang, but in reverse. One is an end of time, the other was a beginning. So if we've learned that information can actually escape the ultimate trap, the ultimate endpoint, what does that tell us about the beginning? Does it mean information from before our universe could have survived the Big Bang? That maybe the Big Bang wasn't a true beginning at all, but just a transition? That's the incredible question Hawking's work leaves us with. a hint that the end of a star might just tell us something about the beginning of everything.